Up to this point, you've learned how to calculate pH, work with Ka and Kb, and understand how buffers resist changes in pH. Now we're going to bring all of this together using titrations. In this video, you'll learn how to read and interpret titration curves, identify equivalence points, choose the correct indicator, and calculate pH at any point during a titration. So let's get started. So here I'm showing a strong acid, strong base titration curve. So for the strong acid, let's say there's maybe HCl, and strong base is sodium hydroxide. Starting off here, this point indicates the H plus concentration with no OH being added. As OH is slowly added drop by drop, the H plus is being consumed and the pH is very slowly rising till we get to this point here. At this point, only 1 or 2 drops of NaOH will send it up here. So halfway in between where this almost vertical rise begins and where it ends, halfway in between, is called the equivalence point. This is where the moles of OH negative is equal to the moles of H positive. It's completely neutralized at this point. So at this point, I would have basically just NaCl in water. The pH is at 7 for a strong acid, strong base neutralization. Now, as I continue to go drop by drop of OH, now the OH is taking effect now, okay? And the pH is going to start rising quickly until we reach the final concentration of the OH. So it becomes very basic. So always look for a strong acid, strong base for the equivalence point to be around 7. Okay, so for a weak acid, strong base, let's assume the weak acid is something like acetic acid. Strong base again, something like sodium hydroxide. I'm showing you with the dotted line a strong acid portion of this curve, and then the solid line, the weak acid or acetic acid. Notice we're starting at a much higher point because acetic acid is a much weaker acid. Also notice that this area here is much shorter than before. And also notice that the equivalence point, or the halfway point between the two curves, is approximately pH of 9. So at the equivalence point, the moles of OH again is equal to the moles of H plus produced by the acetic acid. But the reason that it's at a pH of 9 and not pH of 7 is because of the conjugate base of the acid is fairly basic. So therefore, the equivalence point will be up here around 9 instead of 7. After this point, the OH is now in charge, and the curve should match exactly like the previous slide. Okay, here I'm showing you the reverse, where I'm adding acid to a strong base. And I just wanted to make you aware how the curve looks with a strong base and a strong acid, and a weak base and a weak acid. Again, I have a weak acid, strong base, and I want to point out something called the buffer region. Okay, so initially it goes up, it kind of flattens out in this area here. Okay, as it flattens out, we call this the buffer region. And midway of this buffer region, the pH equals to pKa. That means that I have a 50% HA and 50% A negative. So this demonstrates the Henderson-Hasselbalch behavior. And this is very significant because the pH changes very little in this region. So this is called the buffer region. When choosing an indicator, you have to determine what type of titration you have: strong acid, strong base, weak acid, strong base, so on and so forth, to know basically where the equivalence point is going to be located, so you can choose an indicator that will change color somewhere in this desired range. Here I'm giving you a list of indicators: phenolphthalein, colorless to fuchsia or dark pink. pH range of the color changes from 8.3 to 10. Bromothymol blue from 6 to 7.6. Methyl red, methyl orange. A lot of people like litmus paper, but litmus paper is more difficult to use, and I prefer some of the other ones. Universal indicators is a mixture of several indicators, and it's pretty good if you want a close approximation to what the pH is using a color chart. So quick tips for students: phenolphthalein is the default for weak acid, strong bases like acetic acid and sodium hydroxide. Methyl orange is the default for a strong acid, weak base like hydrochloric acid and ammonia. Also, don't flood your Erlenmeyer flask or your beaker with too much indicator. Only 2 or 3 drops will suffice. The endpoint color is reached when the color change happens. When you add 1 or 2 drops, the color will go from the acid color to the base color. And you want it to get this as few drops as possible where the color lasts. It's not a fleeting color. But when just a couple of drops either direction, then that means that you're right on this portion of the curve here, when only 1 or 2 drops. So that gives you your end point. So always be careful here when you're titrating. Okay, you can calculate the pH of any point during a titration. So what you would do is, first of all, you have to find the moles of H+. So in this one here, 0.100 moles of H+ per liter. And we have 50 milliliters, so I'm going to multiply that times 0.050. That would give me 0.005 moles of H+. We'll do the same thing for the base. Okay, it's a 0.100 moles of OH negative per liter. I'm going to be using 49.049 milliliters. So when I multiply this out, I would get 0.0049 moles of OH. Okay, so I have more H plus than I have OH negative. So I'm going to subtract those two. So if I subtract these two, I get 0.00, let's see, 101, okay? That'd be moles of H plus remaining. Let's take this 0.0001 moles. Let's divide it by the total volume. Okay, so I had 50 milliliters, which is 0.050. And I had 49 millimeters, 0.049. Okay, this would be liters. So if I were to divide this, I would get 0.00101 molar H plus. To get the pH, that'd be the negative log of 0.00101. And that pH will be equal to 3.0. Okay, here's the same problem as the previous problem, except this time we have 2 more milliliters of the base. All right, so as before, we'll calculate our moles of H plus. So we'll multiply it times 0.050. As before, we'll get 0.005 moles of H plus. For the base, 0.100 moles. Multiply this times 51 milliliters. They give us 0.0051 moles of OH negative. All right, so my moles of OH negative is greater than my moles of H plus. So I'm going to say 0.0051 moles OH negative. I'm going to subtract from that 0.0050 moles of H plus. So I get 0.001 moles of OH negative. So we'll take our 0.0001 moles of OH negative and we'll divide it by the total volume. To give me 9.9 times 10 to the negative fourth moles of OH negative. We'll say the POH is the negative log of the OH. So the POH is going to be the negative log of 9.9 times 10 to the negative fourth. So the POH is equal to 3. So the pH is equal to 14 minus the POH. So the pH is going to equal 11. So that shows that before we were here And after adding 2 drops, we were somewhere in this region here. Okay, how much 0.0025 molar sodium hydroxide is needed to completely neutralize 50 milliliters of a 0.0035 molar HCl solution? Let's use the formula volume of acid times the concentration of acid is equal to the volume of the base times the concentration of the base. Since I have one OH and I have one H, I don't have to do anything special. So the volume of the acid was 50 milliliters times the concentration of the acid, which was 0.0035. The volume of the base we do not know. Concentration of the base was 0.0025. Okay, let's divide both sides by 0.0025. So the volume of the base is equal to 70 milliliters. That's how much is required to neutralize 50 milliliters of the given acid. At this point, you should be able to identify titration curves, locate equivalence points, and calculate pH at different stages of titrations. If you can do that, you connect everything from pH calculations to equilibrium and buffers into one complete picture. In the next video, we'll finish the series by looking at solubility and Ksp, where equilibrium shows up in a different way. I'll see you in the next video. Goodbye for now. Thank you.